Hey everyone. So in today's video, I just want to talk about the uncertainty principle and to introduce it in an intuitive and easy to understand manner. So the uncertainty principle was a statement delivered by a German physicist called Werner Karl Heisenberg, who in 1927 stated that it is impossible to simultaneously measure both the position and momentum, which are conjugate variables, of a particle with unlimited precision. Okay, so the uncertainty principle as a mathematical expression is boxed in red here. That is the change, the uncertainty in a particle's position multiplied by the uncertainty in a particle's momentum has to be more than or equal to this very tiny number. Now this very tiny number h, is basically Planck's constant, okay? And the number is approximately 6.63 times 10 to the minus 34 joules seconds. This constant basically represents the smallest quanta of quantum mechanical electromagnetic action, basically. In wave particle duality, when we are describing light as a photon, the Planck's constant basically relates the frequency or the wavelength of light to how much energy it carries. Okay, so it's a very small number. And just to remind you, x is position and p is momentum. Okay, now before we head along, I just want to quickly talk about these things boxed in green. I didn't want the video to be too long, so I'm going to quickly go over these things, and if you want more information on them, then there's plenty of material on the net, or I can make a later video. So the uncertainty principle is directly related to quantum mechanics, which wave particle duality falls under, and that is matter, mainly isolated systems. By isolated systems, I mean single body systems, such as single electrons, or very simple systems such as a hydrogen atom. That is, matter can be described using both particle and wave descriptions. Okay, so matter can either have wave behaviors or particle behaviors. The de Broglie wavelength, also under quantum mechanics, relates an entity's wavelength to its momentum. Now, I say entity because we could either be talking of a pure wave or a pure particle, whether or not they have particle duality, wave particle duality. And everything does have wave particle duality, but some look like particles more than others that look like waves. Okay, so that's why I said entity, and that is the wavelength of that particular entity is equal to the Planck's constant divided by its momentum. So something with a lot of momentum will not be very wave-like, but something with a very small amount of momentum will look more and more wave-like. Photon. So with the advent of quantum mechanics, we stopped talking about light as just a simple wave. Instead, it is a photon, and a photon is a fundamental quantum mechanical particle. All right, so all light are just photons, and photons both have wave-like properties and particle-like properties. Okay. Also, wave function. The wave function is a mathematical description of a quantum state of an isolated system. That is, if I'm traveling to the airport and I produce to you my ID card or my passport, that's basically a short description of who I am and what I am. Okay, this is ID in the quantum world, wave function. Now moving over here, wave-like properties, wave-like behaviors, as we remember from school, are things like diffraction. That is, when light passes through a gap or interacts with an object, it spreads out. Okay, diffraction. And for very good diffraction, now this is very important for what we're going to do in a bit. For very good diffraction, the wavelength of the light must be similar to the gap size or to the dimension of the object that it is interacting with. Reflection, that is when the angle of incidence of light equals the angle of refraction. So, when you look in a mirror. Refraction, that is how light changes direction when it enters into a different medium. So imagine light traveling from air into glass and back out again. It will change direction. Polarization, the fact that light comes in waves that are traveling in every single direction. So you polarize them to make sure you only have plane waves. A good example of this are polarized glasses. So when sunlight passes through some glass and you get glare and you can't see, you can put a polarizing filter to make sure that only light traveling in a certain direction or in a certain plane can get through, so it becomes easier to see. And last, we have superposition. There are many more, by the way, but I just didn't want to write them all. You have superposition, which describes how different waves superimpose constructively or destructively. Then we have particle-like behaviors. Point scattering. Imagine playing snooker and you hit the white ball onto a black one and you scatter the black ball. Instantaneous energy transmission. The fact that in particle behavior, energy is transmitted immediately. It's either you have the energy to make something happen or you don't have the energy to make something happen. Okay. Line spectra. So when we talk about electron energy levels and the fact that electrons in bounded energy levels need a specific amount of energy in order to be promoted to a higher energy level. Straight line propagation, the fact that matter is likely to travel in straight lines. Momentum, the fact that matter is massive, matter has mass, and therefore the product of its mass multiplied by its velocity gives it momentum. Okay. All right. So before we actually head on to explaining the uncertainty principle in an easy to understand way, let's first of all talk about waves, okay, and how the energy of a wave is related to its amplitude, okay, because this is very important in what we're about to do. Okay, so a standard wave equation is this. That was badly drawn, so that's meant to be sine omega t. Okay, and now the quantities that I've just written are y for displacement. Now displacement in this sense describes when light or any wave is traveling through a medium, it deposits energy. And it deposits energy into the particles that constitute that medium. When energy is deposited, they get displaced, they start moving. So this y displacement in meters basically describes how much the medium is moving due to the action of the wave traveling through it. We have A for amplitude, amplitude. That's also in meters, and that describes the maximum displacement. Amplitude is basically maximum displacement. Okay, we have sine, which is a trigonometric function, and then we have omega, which is called the angular frequency. Okay, the angular frequency, and that's typically in rads per second. Okay, another way to write this is omega equals 2 pi f, or it equals 2 pi over the time period of said wave. Okay. Okay, so this is a standard wave equation. All right. Now, we need to understand that waves carry energy. How do we express the energy carried by the wave? Well, let's use mathematics. So first of all, let's differentiate this equation with respect to time. So dy by dt. Now, differentiating this will give us this expression here. Cos omega t. Now, dy by dt, if this is displacement in meters and this is time in seconds, then we've basically got meters over time, meters per second. So the displacement over time basically gives us an assumed velocity of the wave, okay? The velocity of the wave. Now, what we know from secondary school physics is that the kinetic energy. Now, kinetic energy is very important here because kinetic energy is the energy that is required for anything to happen, okay? So if anything is moving or you need an event to occur, you must have kinetic energy, right? Now, kinetic energy is equal to half mv squared. So an object or an entity's mass multiplied by its velocity squared multiplied by a half gives you its kinetic energy in joules, okay? So essentially, we can basically have the kinetic energy of the wave. Now, because waves don't have mass, okay, we're going to make a sort of approximation. And we are just going to say that if mass is constant and the half is constant, then the kinetic energy of the wave, so Ke, is just simply going to be proportional to v squared. And if we write this in terms of our wave expression here, then our kinetic energy is similar to this whole thing squared. That is the amplitude squared multiplied by the angular frequency squared multiplied by the cos function also squared. Okay. Now, we have a couple of quantities here that are basically constants. Okay. So angular frequency is basically a constant. That doesn't change. And this thing over here is basically a constant. That also should not change. I mean, it can change depending on the kind of waves that you are using, but for now we're just going to say that these are constants. Therefore, the kinetic energy of a wave is directly proportional to the amplitude squared. The amplitude in wave theory describes how big the wave is or how bright the wave is. Okay? Christopher Huygens, who was a physicist in Isaac Newton's time, basically described waves as wave fronts that propagate through space. His description said that the amplitude of the wave was basically the size of the wave front. So the larger the wave front, the more energy the wave could carry. Okay, and this falls in line with the wave idea, the wave-like idea that the amount of energy on the wave is directly proportional to its amplitude. Okay, right. So the way we are going to describe the uncertainty principle is to imagine that we are measuring an electron. Okay, and we aren't measuring this electron with rulers or expensive computers. We are measuring the electron with light. Okay. Now, the best way to measure things in this universe is to use light, because light carries energy and it carries momentum, it scatters, it can be transmitted and received, and it travels at light speed. Okay? So let's imagine that we have an electron in the vacuum, okay? In the void of space, deep space, okay? It is under no external, there are no external influences, there are no forces on it. It's just an electron moving with a speed v, therefore it has momentum. So I'm going to say that the electron has a momentum p equals m vx, okay? So it's moving with some velocity in the x direction, and it has a position x equals x. Yep, it has a position x. Okay, so at the time we measure this electron, it is moving with a momentum mvx, and at the exact instantaneous time that we measure it, it occupied a position x. Now over here, let's assume that we are over here, okay, and we have a loudspeaker that is basically shooting out different kinds of waves, okay? And let's just call this a transmitter. Okay? Now this transmitter is shooting out both high energy, by the way, I said waves. I shouldn't have said waves. I should have said photons. So this transmitter is shooting out light photons, okay? Now the kind of photons that it's shooting out are high energy and low energy photons, okay? Now I say high energy and low energy photons because in quantum mechanics, the energy of a photon is directly related to its frequency or wavelength. Okay, so the larger the frequency of the photon, the more energy it has. The larger the wavelength of the photon, the less energy it has. Okay, and I'll just box that for reference. Okay, so let's assume that we are shooting both low energy photons. So I'll denote these using red pen. And we are shooting high energy photons, and I'll denote these using blue pen. So I'm going with the convention that blue light is like UV and above and is very energetic, and red light is infrared and below, which is not so energetic. Okay, so one last thing is that blue photons have high energy. They're highly energy, so large F and low wavelength, whereas the red photons, so these are lower energy and we have low F and large wavelengths. Okay, now down here we're expecting that some of the scattered light, so the light will interact with this electron. Okay, so let me just label this again so that we're not confused. This electron, and we have a receiver. I'm going to shape this receiver like as if it's a Faraday cup. Okay, and we are us also here, and this is our receiver. Okay, transmitter, receiver, and we are going to get some of the scattered light coming to our receiver, and I drew them in a dashed fashion to show that they have interacted with something, and what we are receiving is after the main event. Okay, so that's our scenario. We are measuring an electron in deep space under no external forces or influences using light photons. Now, a bit of information, extra information for you, is that the mass of the electron is approximately 9.31 times 10 to the minus 31 kilograms. So an electron is tiny, okay? It's very, very tiny. It's a fundamental particle, a lepton, and it's very, very tiny. The radius of the electron is of the order 10 to the minus 18 meters. So it is tiny, okay? Very, very, very tiny object. Now, let us shoot light at said electron and see what happens. Okay, so first of all, let us shoot red light. So let's shoot red light. The red light will interact with the electron, scatter, and come back to us. Okay. Now the point is that we are going to measure the resulting wave function. We are going to measure the resulting wave function of the backscattered light. Okay. Our y-axis is going to be the amplitude of the wave function. So the wave function is psi, and the x-axis is going to be the position. Okay. Now, when we use red light, we are going to get this pattern here. Okay. So you can pause the video and just try and describe it in your head to see what it might represent. Bear in mind, I'm not a very good artist, so these all have to be the same height and the same depth, and they need to be equally spaced. Okay. The first thing we notice is that the amplitude of the wave function is clearly defined. Okay, the amplitude of the wave function is clearly defined. Since the amplitude of the wave function is clearly defined, so A is clearly defined. Since A is clearly defined, and we know from wave theory that the energy of a wave is proportional to the amplitude squared, it means that it is very, very easy to pinpoint or measure with precision the momentum of the electron, because momentum is directly related to the energy. In fact, as far as I can remember, the kinetic energy of an electron is equal to its momentum over that. So this means that if mass is constant, then the momentum of any particle is directly related to the kinetic energy. So if we can clearly define the amplitude of the wave function, it means we can measure the momentum of the electron with great precision. Okay? However, what do you notice about the position of the wave function? Look here. The position of the wave function is spread all throughout space. This means that we have a large uncertainty in position. Okay, we don't know where this wave function is localized. It could be anywhere in space. We don't know. Okay, we have no clue, and this is because the the wavelength of the red light is a lot larger than the size of the electron, so it didn't scatter much. It just transferred a bit of energy and came back, and we got a wave function which told us about the energy of the electron. But because there wasn't a lot of scattering, okay, due to the lack of diffraction, we couldn't possibly pinpoint where the electron is or was in space. Okay, so the uncertainty principle is still obeyed. That is, the uncertainty in position is way up there. The uncertainty in momentum is way down there, and it is still going to be more than or equal to 2 pi over lambda, which still happens to be a very small number. Okay, so we've just shot red light. Okay, now let us shoot blue light. Let us shoot higher energy light. So now let us shoot blue light. Okay, so we're going to shoot blue light. The resulting wave function that we get is going to look something similar to this. Okay, so let me just draw my axes. That's position once again, and that is the amplitude of the wave function, and that's this whole thing is wave function psi. By the way, I'm not the best drawer, but I'll try. We get something that looks like that. Okay, now what do you notice? Well, the first thing we notice is that the amplitude of the wave function is at different heights and troughs. It is, since we can't fix the amplitude, we cannot fix the momentum. Okay, so amplitude is not clearly defined. Okay, so the change in momentum, the uncertainty of momentum is very high. Okay, however, look at what's been localized. We've been able to localize the wave function in position. Okay, we should be able to accurately pinpoint the electron being somewhere in this region here. Okay, So even though we were not able to pinpoint the momentum with precision, we can see that the wave function is localized in position. Okay. Now the reason for this is because when we shoot blue light, so let's say we were shooting X-rays or gamma rays, they behave like particles, okay? And even though they behave like particles, they still have very tiny wavelengths. And their tiny wavelengths are pretty much similar to the size or the radius of the electron itself. So there's going to be a lot of scattering. But because they carry a lot of energy, there's going to be a lot of energy transferred. We don't know how this energy will be transferred. That's why when the wave comes back, we don't know what carried what energy at what time. Okay? This is why we have barely any information on the energy of the electron. But because the diffraction was so good, the photon scattered back and gave us a very localized wave function. So once again, Heisenberg's uncertainty principle is obeyed. That is, the uncertainty in position is way down, and the uncertainty in momentum is way up, and that is still going to be more than or equal to Planck's constant divided by 2 pi. I hope you learned something from this video. Thank you for watching.